Okay, so welcome to our 16th class of Computer Architecture and Organization. So in this class, we are going to discuss about a concept called Endians. Endians, not Indians, E-N-D-I-A-N-S, Endians. Okay. So in the previous class, we have discussed about load operation, store operation, isn't it or not? So in this class, we are going to discuss about these Endians. Okay. So actually, what are these Endians means, and what is the purpose of these Endians? Okay, that we are going to discuss now. Okay. See, if I want, in the last class, we have discussed about these two instructions. What are the instructions? Load instruction, and store instruction. Isn't it, Anna? So, if you observe carefully, what is meant by a store instruction? Okay, store instruction is nothing but we are going to transfer the data from a register into a memory location. Isn't it, Anna? That's what we have taken an example of moving your house from one place to another by a lorry. Okay, so what is meant by loading? Taking all the what you will call goods from your home into the into the lorry is called load, and whenever you reach the destination, you will take all your materials from that lorry and you will place it into your home. That is called store operation. So we are having load and store operations. Okay, so what is meant by store operation? Store operation is nothing but transferring of the data from the register into the memory location. Transferring of the data from the register into the memory location. This phenomena is called store operation. Okay, see, then there are two ways of storing the instruction from register to the memory. There are two ways of storing the value or contents in a register into the memory. Those two ways are nothing but big endians and little endians. Big endians and little endians. What does they mean? Before going to this concept, I will explain you with a small example. See, this is one of the examples for big endians. Before going to discuss what is meant by big endians, I want to give you one clarity. That see here, A plus 1, A plus 2, A plus 3 are there now. These are the memory locations. Here also, A plus 1, A plus 2, A plus 3 are there now. These are the memory locations. Okay. What is the size of each memory location? The size of each memory location is 8-bit. What is its size, Amma? 8-bit. Okay. Next. I have told you previously, and I am once again revising you that whatever the values we are going to write, we will write in a hexadecimal number system. That means whatever the, whether it is an FPMC, that means 8086 programming or 8051 programming, whatever the programming, what we used to write as far as our EDs, as far as our electronics point of view, okay, we used to represent a number in hexadecimal number system. Whereas in C, you used to represent a number in a decimal number system or something like that. But in our, what you will call microprocessor or microcontroller, if you want to give any input value, okay, the input value number should be represented in hexadecimal number system. What is the system, Amma? Hexadecimal number system. But you know very well that computer can not understand hexadecimal number system. Computer can understand only one number system, that is binary number system. That means it consists of values in the form of zeros and ones. The binary number system consists of values in the form of zeros and ones. Our computer can understand only the binary number system. It does not understand the other number systems. Is it clear? Okay. So then what it will do? It will convert those number systems into the binary form. That is the another concept. See, but what is the thing I want to say is, see here the size of each memory location is 8-bit. What is the size of each memory location? 8-bit. Okay. Next, see, our computer will store the data. Though we write the input values or though we give the input values in hexadecimal number system, our computer or our processor, our controller, whatever it may be, it will store the data in the memory in the form of binary numbers. In the form of binary numbers. That means in the form of zeros and ones. I think you all are very much familiar about the conversions in your STLD. Okay. So as far as STLD is concerned, so in order to convert a single hexadecimal number, you need 4 binary values. isn't it or not? In order to convert a single hexadecimal value, you need 4 binary values. Okay, so hexadecimal to binary conversion. Hexadecimal radix is 16, binary radix is 2. So 2 power 4 is 16. That means in order to convert each hexadecimal number, you have to represent it with 4 binary values. Okay, now here also these numbers, whatever those are coming 0A, 0B, 0C, 0D, these all are in hexadecimal. As they are in hexadecimal, you can get A, B, C, D like that. A means 10, B means 11, C means 12, D means 13. I think you all are familiar with it. Okay. Okay. Now we are coming to our concept. See, before coming to our concept, what is the thing you need to know is whatever the numbers we are going to represent in our processor or controller, we used to represent them in hexadecimal. Okay. But our computer or processor, it is going to convert those numbers into the binary form and then it will store in the memory. Okay. The size of a memory location is 8 bits only. That means the size of a memory location is 8 bit only. Okay. So here, alpha or A plus 1, A plus 2, A plus 3, these are the memory location addresses. A means 2000 means next address will be 2001, 2002, 2003 and so on. Okay. Now I am coming to my point. What is meant by big endian and what is meant by little endian? So here itself, if you observe clearly, see in the register, these things will be LSB, least significant bit. And if you consider 0D, H, if you write this hexadecimal into binary, used to represent with 1 minute, I'll show you. X. Okay. Yeah. See here 0A, 0B, 0C, something like that they have given now. It is in hexadecimal. When you convert that particular into binary, how can we write? 0 can be written as 0000 and A means 10, 1010. I think you are very much familiar. Next 0, 0000. Next B 11, 1011. Isn't it or not? Next 0000. Next A is 10, B is 11, C is 12. 1100. Next 0000. Next D 1101, like this. Okay. So if you observe, this is the way of writing. Okay, 4 zeros means 0000. Next A means 1010. Next 4 zeros. Next 1011. Like that I have represented. Okay. I have told you previously that whatever we write in hexadecimal, it should be converted into binary form. Next, what is meant by big endian and what is meant by little endian? What is meant by big endian and what is meant by a little endian? Okay, big endian means, see here, this will be represented as most significant byte. Byte means 8 bits na. These 4 and these 4 all together. Oh, sorry. So if you observe these 4, 00001010, that means 0A will be considered as most significant byte. Next significant is 0B. Next byte is 0C. Next byte is 0D. Isn't it or not? Okay. So if you observe carefully in the big endians, in the starting memory location, okay, what is the value we are going to store? We are going to store the uppermost byte. That means 0A. Okay, na? In the next memory location, we are going to store the next upper location. Okay, that means in the starting memory location, we are going to store the value that is present in the topmost or most significant side. Later on, we used to go store in the next significant value in the next memory location. Afterwards, the next value in the next memory location. Okay, these phenomena is called as, it will be referred as big endian. That means the highest value, the value that is present in the most significant side, that is simply to say the value that is present in the topmost left side, that value is going to be stored in the first memory location. The next topmost value 0B is going to be stored in the next memory location. The next topmost value 03 is going to be stored in the next memory location. And the last value is going to store in the last memory location. I cannot say it is the last memory location, but as far as these things are concerned, this is the last memory location. Okay, this phenomena is called big endian. Whereas coming to little endian, if you observe carefully, here, see, this 0A is there, na, topmost value. This is not going to store in the first memory location. Here, what is going to be stored in the first memory location? The most significant, least significant byte, not most significant byte. The least significant byte that is present is there na 0D. This is going to be stored in the first memory location. The next 03 is going to be stored in the next memory location. The next 0B is going to be stored in the next memory location, and 0A in the last memory location. See, if you observe these two examples, see in the first memory location, here the most significant byte is being stored. Here, in the first memory location, the least significant byte is being stored. Okay. Next, the next value in the next memory, the next value in the next memory, like that. So this is the difference between big Endian and little Endian. Big Endian and little Endian. Okay. I think you all are very much clear with this example. Okay. The most significant byte, if it is stored in the first memory location, the next below significant byte is stored in the next memory location. If this storing goes on like that, then it will be referred as big Endian. If the storage is in a reverse order, then it is called little Endian. Okay, I think all of you are clear. Okay. So we'll just come to the definition. What is meant by big Endian and what is meant by little Endian? See, I think you all are very clear with that example. Now we are coming we are analyzing the definition. What is meant by little Endian? Storage is starting from the least significant byte. That's what I have told. For little Endians, the storage is starting from least significant byte. Isn't it or not? For little Endians, see, the least significant byte is going to be stored in the first memory location, followed by least significant byte, followed by next least significant byte. This phenomena is called little Endians. Whereas coming to the big Endians, storage is starting from most significant byte to the and finishes with the least significant byte. That's what we have told in the example. Here, the storage is starting from most significant byte, followed by next most, and ending with the least significant byte. This phenomena is called big Endians. And starting with the least significant byte and ending with the most significant byte, this phenomena is called big Endians. Sorry, little Endians. That is the difference between little Endians and big Endians. Okay, big Endians means starting with the big number. Little Endians means starting with the little number. Okay, that is the thing you have to understand. Here, this is one more example of saying, see, I have a value of 1FC3. This is a hexadecimal number. Okay, if I follow little Endian, these are the address locations: 0th address, first address, second address, third address. This is LS means least significant byte, MS means most significant byte. If I follow little Endians, what is the thing that is going to be happen? That means, see, the first value or the one is going to be stored in the first memory location. Okay, see, 1, next memory location F is going to be stored, next memory location 3, and next memory location C. If I follow big Endians, then the alternate order is going to be performed. That means in the first memory location, if the memory location is going to be start with 0, I used to store C. In the next memory location 3, next F, next 1. So that is the difference between big Endian and little Endians. Next one, subprogram or subroutine. What is meant by a subprogram or subroutine? See, before discussing this concept, for example, I have a big program. I need to develop a big program. Okay, or in the next 1 or 2 years, you are going after completing your BTech, you may become a programmer, where you need to develop big programs for different tasks. Okay, see, you are going to develop a program. In that particular program, you need to perform addition some 10 times. You need to perform subtraction some 20 times, and you need to perform some multiplication operation some 10 times. See, you are going to develop a program where you need to perform addition on not the same numbers, but the same numbers may different. But you are going to perform addition in your program some 10 times. Similarly, you are going to perform subtraction in your total program some 15 times, and multiplication some 20 times, like that. Okay, see, for writing the addition program, it takes, let us assume, for writing the addition program, it takes some 10 instructions. For writing the subtraction program, it takes some 10 instructions. And for writing the multiplication program, it takes another 10 instructions. Okay, let us assume if I used to write those 10 instructions at 10 times in addition, 15 times in subtraction, and 20 times in multiplication. What is the thing that is going to happen? Totally, how many instructions I have to write? 10 into 10 for addition, that means 100. 10 into 15 means 150 for subtraction. 10 into 20, 20 tens are 200 for multiplication. That means 200 plus 150 plus, if not, I will just show you. See, 10 into 10, 100 for addition plus, so this is plus 10 into 15, 150 for subtraction plus 10 into 20, 200 for multiplication. Totally, how many instructions I need to perform? 200, 300, 450. 415, what you will call instructions I need to write for my program only for the sake of performing addition, subtraction, multiplication. Addition for 10 times, subtraction for 15 times, and multiplication for 20 times. Okay. Here, this is very, first one, time consuming, and if I write these many instructions these many times, it will occupy a lot of memory, and for writing these many instructions it takes a lot of time. Okay, and the processor also takes a lot of time for execution also. Okay, so these are many problems. In order to overcome these problems, I have gone for a, or not me, the developers has gone for a solution, because if they anywhere there is a problem, there should be a solution. Okay, so there is a solution to overcome from these kind of things. What is these kind of things? Where I used to write the same instructions multiple number of times. Okay, that is my problem. It is not a problem. So where when I encounter with a program, or whenever I am developing a program, there I need to repeat the same type of instructions for multiple number of times, because in my entire program I need to perform addition on different numbers for some 20 to for some 10 times, and subtraction on a different numbers for 15 times, and multiplication on different numbers for 20 times, like that. Isn't it or not? So here, what is the thing that is that I should one should remember is, if I am go on writing those instructions, the program is going to be very lengthy. It will take lot of time. It will take lot of time for execution. Complexity of the program is going to be very high. I cannot detect the errors easily. It will be a very much headache to me. Okay, in order to overcome, I cannot. I haven't produced any slideshow now. Wait, slideshow. 1 minute. Sure. 1 minute. Slideshow I have to show now. From current slide. Yeah, you forgot to do that. Okay. So now, in order to overcome from this problem, what I am doing means, I will write the addition instruction only one time. I mean, that means I will write the additional program only one time. I will write the subtraction program only one time. I will write multiplication program only one time. That means I will write only 3 programs. That means if a program has 10 instructions, altogether I will write only 30 instructions. 10 for addition, 10 for subtraction, 10 for multiplication. Okay, that too where I will write those instructions, or those things means I am not going to write them in the main program. Okay, I think you all have C program. Okay, in C program you are having a topic called functions. I think did you all remember that topic? Functions. What are mean by functions? Functions are nothing but the small part of the programs that are written separately from the main program. Isn't it or not? Okay, I think you all are aware with the concept called functions. Functions are nothing but a small part of the programs that are written separately from the main program. The same concept of functions is applied here also. In our programming, we are having subprograms or subroutines. What are mean by subprograms or subroutines? The same concept of functions here also. Here also we need to write the same instructions multiple number of times. In order to overcome from this difficulty of writing the same instructions multiple number of times, what we are going to do is we are going to write the instructions which are going to be repeated multiple number of times in our main program. We are going to write those instructions separately from the main program, and we used to give a name to that particular subprogram. See, if I want to perform addition 20 number of times, I used to write those particular addition instruction separately from the main program, and I used to give some name ADD like that. Okay. Similarly, I used to write a program for subtraction separately from the main program, and I used to give some name SGB like that. Okay. So these small programs which are written separately from the main program, those are called sub-programs. The name itself, it is very much clear. They are sub-programs or subroutines. Okay. The main purpose of writing or developing these sub-programs is in order to reduce the complexity of the program, reduce the number of instructions of the program, reduce the memory space occupied by this program. So by using this concept, if I write, for example, in my program, there is a necessity of addition for 30 times, 40 times, 50 times, I don't bother. Similarly, if I need a subtraction for 30 times, 40 times, 50 times, I don't bother. Once if I write a program, that is enough. Okay. Whenever I want to perform addition program in my main program, then I will call that particular subprogram. So I will show you in the next slides. You can easily observe. Okay. See, this is the main program. Okay. I used to write subprograms or subroutines. Okay. So that's what I have told now previously. Where is it? Erase. Okay. See here it is subroutine, not subroutine. It is SUBROUTIN, subroutine. It is some mistake. Okay. See, for example, here assume this is an additional program. This is a program of addition. Okay. Whenever my main program, whenever I want to perform some addition operation, then I will call this particular subroutine. I will give some name to this particular subroutine. For example, I will give Mohan Krishna. Mohan. Okay. Whenever or else for your easy understanding, let you assume that I have given a name called addition, ADD. Okay, ADDITION, addition for this subprogram. Okay. Whenever I want to perform addition in my main program, okay, I won't write all these instructions in my main program. Okay. I will develop a subprogram separately from the main program, and I will use this instruction call space this name of this subroutine. For example, consider the name of these. For example, consider its name as something like addition. Consider it as ADDITION. It is the name of this subprogram or subroutine. Okay. So, for example, I want to perform addition here. Okay. Then what I am going to do? I will use the instruction called call space. Call space. What is the name of this subprogram? Addition. So I used to write call space addition. Okay. Whenever I use this instruction, then what is the thing that is going to happen? Means, see what I have written. I have used the concept called call space addition. Okay. Whenever I use this instruction, wait 1 minute. Control Z. Here, for example, I will make you much more visual. Yeah. For example, this is addition, ADDITION. This is one subprogram. This is not written in the main program. This is written separately from the main program. Okay. Next, this is my program, main program. Here I want to perform some addition operation. Then what I am going to do means I will use an instruction called CALL. That means call. Okay. And I will give the name of this subroutine. What I have given, what is the name allocated to this subroutine? Addition. Okay. So I used to write like this. Call space ADDITION. Call space addition. Whenever I use this instruction, then what is the thing that is going to happen is my controller. What is it? My controller. Okay. Will transfer from, see, actually my controller or my processor, it is going to execute first instruction, second instruction, third instruction, fourth instruction, like that. Whenever my controller comes to this particular instruction, it will see call. Okay, we are having two important instructions called call and return. Similarly, push and pop. Okay, here whenever it encounters with call instruction, call means to పిలవటం అని అర్థం. అవునా? ఇది పిలిచిద్ది. ఎవరిని పిలిచిద్ది? మనం వాడి పక్కన ఎవడి పేరు అయితే పెట్టామో వాళ్ళని పిలిచిద్ది. ఇక్కడ if you observe here, what is the name I have given? Addition. Okay, then it will understand that addition is a name of a subprogram. Okay, it is the name of a subprogram or subroutine, and it will search this where this particular subroutine is present in the memory. Because it is not written in the main program, it is written separately, it may be somewhere. Okay, then our processor will search where is the subprogram with name addition. Okay, then somehow it will find this subprogram. Okay, then what it is going to do, it will transfer from our main program to this subroutine addition. It will not execute the next instructions. It will just transfer its execution from this part to this particular part. Okay, and it used to execute all the instructions that are present in this subprogram. Okay, for example, it has some 10 instructions. It used to execute all the instructions. Okay, once execution of all the instructions are over, see, one thing you should keep in mind is the last instruction for any subprogram or subroutine should be written. Okay, what is the purpose of this one is, this indicates that your task is over. See, this is the subprogram written for addition. That means it consists of some instructions which are useful for performing some addition. Okay, so in the last instruction should be written, which indicates that your execution or your task is over. Now you can leave. So whenever our processor or controller encounters this return instruction, it needs to return. From where it has to return? From where it came. That is the concept of returning now. For example, if I purchase any book from a shop, and if I want to give return, I have to go to that particular shop and I have to give return. Isn't it? Here also the same concept. Here, when I will go return means it has to return to a place from where it came. From where it came, actually, it came from the main memory. So it has to be written to the main memory itself. So in the main memory also, from where it came, from this instruction call space addition, from this instruction it came. Now again it will come to the next instruction. And it will execute the rest of the instructions. See, after executing some instructions, again I have encountered same call instruction. Here also, for example, assume call space addition. Okay, then also what is the thing that is going to happen? Again my controller goes to this particular subroutine. It will execute all the instructions. Once it encounters with the return instruction, it will return to the main program to the next instruction, but not this instruction. Because if it comes to this instruction again, what is the thing that is going to happen? It used to go to this particular subprogram again, and it used to execute all the instructions, and again it will come. Then you will come again also the same thing is going to happen. Goes here, execute all the instructions, again it comes here. Then it will become infinite loop. What it is going to become? Infinite loop. Okay, so in order to overcome from this problem, whenever there is a return instruction, it will return to the next instruction but not the current instruction. Is it clear? So this is the concept of subprogramming or subroutine. Subprograms or subroutines, what does they mean? They are a small part of the programs. They are not written in the main memory. They are written separately from the main memory. One main program may contain hundreds of subprograms, because my program may need addition, subtraction, multiplication, division, ascending order arrangement, descending order arrangement, like that, so on. Tasks are there in my main program. Then I can write a subprogram for each and everything. Okay, so one main program can contain hundreds of subprograms. There is no limit for that. Okay, but when will we use or when will you write subprogram means whenever there is a repetition of same instructions multiple number of times. Whenever there is a repetition of same instructions multiple number of times, then only you will write this subprogram or a subroutine. If not, we don't write. It is not required. Okay, I think you all are familiar, clear with this concept now. Okay, so once I will say the definition, once I will read out the definition. Okay, not this one. Yeah. See, the smallest program part of the small part of the program that is written separately from the main program. That's what we are discussing until now. Is called as subprogram or subroutine. In subprogram or subroutine, we have two main instructions. One is call, return. What is the purpose of this call instruction? Whenever you want to call any subroutine, then you will go for this call instruction. See, whenever you want to call some other instruction, then you will go for this call. Okay. The last instruction for the subroutine will be return instruction. So we are having call and subroutine return instructions, and we are having two more instructions called push pop. Push and pop. These are the instructions that are used in the stack. Isn't it or not? We have discussed. We haven't discussed about the stack now. In the next class, we are going to discuss about stack and queue. Okay. See, these push and pop instructions are going to be mostly used in the stack. Why? What is the reason? Means, see, I will explain. See, I have given here arrow marks very easily. Okay, and I have told that whenever I call some call space addition, okay, then automatically our main program is going to our controller is going to be transferred from main program to that particular subroutine, and it uses to execute those instructions. I have told like that. It is well and good. But see, once if I write return, okay, how can it return to the next instruction? How can it know? See, for example, if someone, you or me are there, okay, we will, I, for example, consider myself, I am human, I have at least some common sense. I don't say I have a much more common sense, I have at least a minimum common sense. So that I can remember my home, my family members, my surroundings like that, okay. Whenever I comes, and my college also, and the route which is to be traveled, okay. So every day I used to come to the college, okay, and I will attend my duties, and in the evening I will go to my home, because I am a human, I have common sense, I know where the home is, I know the route how to reach my home also, okay. But it is a computer, you don't have any common sense, okay. How can it goes? See, okay, whenever you call and you give some name, it will search and it will go here, it is well and good. But whenever you write the return instruction, how can it return to the next instruction? Does it have any common sense? It does not have, no. So what is the thing that is going to happen means, see, whenever you write a call instruction, the controller is going to transfer from here to that particular subroutine. That's what we have discussed now. Before transferring from here to subroutine, what it is going to do is, it will store. It will store. What it is going to store? It will store the values. It will store the address. It will store the address. Whose address? The address of the next instruction. See, before it leaves from this main program to subprogram, the controller or processor will store the address of the next instruction in the stack by using push operation, because push operation is nothing but inserting the data into the stack. Okay, next, once it encounters with the return instruction, okay, it does not come directly to the main program. Whenever it finds return instruction, it will go to the stack, okay, and there it will take the value which was being stored by it. Previously it has pushed some value, no? Now it will pop out a value and sees from where it see where it has to go now. It is just like Gajini. I think in my inter, the Gajini film came. Okay, if you know, if you are also aware, then it is well and good. In the Gajini, he has some short-term memory loss like that. So he used to write everything in a paper. Here also, you don't have any common sense. So what it is going to do, whenever it goes from the main memory to subroutine, it will store the address of the next instruction in a stack. Okay. For storing the address, we use push operation. Push operation means inserting the data into the stack. Okay. Once it completes the execution of all these instructions, whenever the return instruction comes, then what it is going to do? It will just goes to the stack and pop the value that was stored. Okay. And again, it goes to the next instruction and executes the program. This is the concept. Okay. I think you all are clear now. Okay. So this is the, and in the next class we are going to discuss the next topic. Okay. This is for this step.